Hi, everybody. Thank you for joining us for how to create a secure development lifecycle for firmware presented by the UEFI Forum. We'll give it a couple more minutes and then we're going to go ahead and get started. Thank you. All right, I'm going to pass it off to Brian Richardson, who will be our moderator for this webinar. Go ahead and get started, Brian.
All right, hello everyone. My name is Brian Richardson. I work with Intel Corporation on firmware ecosystem engagement, but today I'm going to be serving in my role as the chair of the Industry Communications Work Group under UEFI. I want to welcome everyone to our webinar on how to create a security development lifecycle for firmware. I'm not a security expert, so I invited a few to come along today. We have Eric Johnson from AMI, Dick Wilkins from Phoenix, and Tim Lewis from Inside. Their CTO was supposed to join us today. Unfortunately, he had a different commitment come up, so Brent Holtzclaw, a security researcher from Intel, is going to come and help present some of his materials. So I want to start the baseline by describing the main topic of today, which is a secure development lifecycle, or SDL. SDL is a process that was originally pioneered by Microsoft, and it's for developing demonstrably more secure software. It improves the capability for developers to support, design, develop, test, and release secure software. It generally follows a cycle of 7 elements: train, require, design, develop, verify, release, and respond. We're not going to go into detail on all of those elements today. You could spend days going into secure development lifecycle and how it applies to software. It's pretty well documented. The thing that we want to cover today is applying SDL to firmware, specifically how SDL can be applied to UEFI products. This means you have to understand design elements unique to platform firmware, and firmware is kind of a special beast in the world of software. So we want to cover 4 specific areas: secure design, secure coding, testing, and the response to security vulnerabilities, and show how those 4 areas have to be slightly adapted from your standard secure development lifecycle for software when you're dealing with firmware products. Now, as we cover the topics, since we brought along a couple of experts, you're bound to have questions. You can submit those questions in the chat window as we go along, and we'll get some help at the end picking some of the top questions and addressing those in the Q&A section. If we don't get to your question today, we might address it later on. We do blogs at uefi.org, and a lot of times what we do is grab questions that weren't addressed in webinars and bring them up in follow-up blogs. So first, I want to start with Dick to talk about secure design and where to begin. You can't really have a secure design unless you understand what your security threats are. So Dick, where do we tend to start in secure design? Oh, I'm sorry. this is Eric's section. I misread my notes. So Eric, when you're designing secure design lifecycle for firmware, where do you typically start out?
So you really can't start considering the security implications of your design until you understand what your threats are. So the first thing that you have to do is to create a threat model. So what is a threat model? I have a definition from Wikipedia, but basically it's a document that describes your system and the different ways that an attacker can potentially exploit vulnerabilities in your system. And you create a diagram as well that helps you to view the system and understand each of the potential areas of attack. Next slide, please. So why should you create a threat model? Well, as we all know, firmware has become a very attractive target for security research. That's the start of the root of trust. So if the firmware has been compromised, any software that runs after that is also potentially compromised. You can no longer trust it. And because the firmware is able to initialize runtime services that are invisible to the OS, it's possible to have malware embedded in the firmware without the OS even being able to detect that something is wrong. Another problem is that firmware is not very often updated by the end user. I know most of my friends have no idea that firmware even exists. So the attackers have years and years to find the vulnerabilities in your firmware, and chances are you're only going to have 1 or 2 opportunities to deploy updates for that system in the future. So a documented threat model also helps during your QA process. It gives you an idea of things that you need to test and look for as you're validating your software. And it's also great for onboarding new hires. You can have them look at the threat model and other design documents and understand how the system was designed before they actually start digging into the code. And of course, if you're getting audited by some of your suppliers, or I'm sorry, by some of your customers, it's quite probable that they're going to ask you for your security documentation as well. And so it's quite useful during audits. So the threat modeling process is a cycle. The first thing that you need to do is define your requirements. And then you diagram your system, you identify the threats, you mitigate them, and then you validate that the mitigations are correct. And the reason that this is a cycle is that anytime you add new functionality or you fix a bug, and especially a security vulnerability, there's a chance that you may have changed some assumption that was made during your threat modeling process, and you need to go back and look to make sure that the changes you made didn't invalidate something in your threat model. So let's start with the first step, which is defining the requirements. So hopefully we all know how to generate a valid requirement. I have some information here on the slide if you're a student or otherwise new to engineering. But basically there are 3 different types of requirements that the system may have. It can be functional, non-functional, or a derived requirement. So you may have a security requirement specifically for firmware that requires you to have the ability for the end user to set an administrator password. You may also have a requirement that says they should be locked out if they fail to enter the password correctly. And a derived requirement would be that you decide that after 3 lockouts or 3 incorrect password attempts, that's when you lock them out of the system. So I'm not going to go over the rest of this slide. It's just there for informational purposes, but it's just information on how to make sure that your requirements are correctly defined and something that you can actually implement and validate during your development process. So in order to actually create a model of your platform, you need to understand some concepts such as what a trust boundary is. So a trust boundary is basically any edge or interface where data or interaction from an untrusted source or a less trusted source is being handled by something that is more trusted or at a higher privilege. So as you cross a trust boundary, the threat is that the untrusted entity is able to escalate its privilege and do things that it wants to do as if it were the trusted process. And then there's also the risk that they may send in a request and get out confidential data that they shouldn't have had access to. So those are the main threats when dealing with trust boundaries, is that you disclose information or elevate privileges. So once you understand what a trust boundary is, you can actually sit down and create a platform diagram. This diagram here comes from the UEFI secure coding documentation. And basically what we have here is a UEFI boot process where you start out with the ME or PSP or some other trusted entity down in the bottom right corner. And then you move across time to the right until eventually you get to the OS load. And you'll see across the bottom here that we have an arrow going from more trusted to less trusted. So you can see that as the boot process occurs, you move into different areas of trust. So during SEC and PEI, you're only running your firmware code, which hopefully you've measured before you started executing, and you know that it's valid and that you can trust it. But once you get into BDS, you may load a third-party option ROM or otherwise do something that calls into the more trusted original firmware and could potentially do something malicious. So you can see that we have a trust boundary here at the end of Dixie. And then again, after BDS is complete and you go to ready to boot, you may go into the BIOS setup or the shell or actually load an OS, and you again cross trust boundaries. And unfortunately, because of runtime services, the threat to firmware doesn't end after the platform boots. So the OS could use a system management interrupt to basically send data into management mode and potentially do something that is dangerous to the system. So even after the OS loads, the firmware still has to worry about making sure that the threat model is correct and that we're properly mitigating any sort of attack that could come from the OS level. So once you're done with the diagram, you can sit down and identify the threats that could potentially attack your system. So these can be, for instance, buffer overflows. They can be a variety of attacks that we'll discuss later in this presentation that could somehow compromise the firmware. And I want to point out here also the threat modeling technique that we're using here is the STRIDE method. There are a bunch of different ways that you can do threat modeling and also respond to threats. And I provided a link to Carnegie Mellon University's guide to threat modeling. It has 12 different methods of threat modeling, and also the advantages and disadvantages to each model and what types of security threats they are especially adept at protecting against. So once you've identified these threats using whatever technique you're going to use, you need to categorize them so that you can decide how they handle them. So for the STRIDE model, we worry about people that are trying to perform a spoofing attack, tampering, repudiation, information disclosure, denial of service, or elevation of privilege. So to give you an example of some of these attacks and how they are specifically applied to firmware, we can think about spoofing as someone being able to pretend to be the OEM or an administrator after the system is shipped. If I'm able to somehow put it back into manufacturing mode, as an example, and pretend to be the OEM, I could potentially change settings that were not supposed to be changed. Or if I can somehow pretend to be the administrator, again, I may be able to disable UEFI security features. For tampering, the attacker is most likely going to want to modify your firmware image on the flash part so that when you boot, they're able to inject their own untrusted code. And they could also potentially tamper with the S3 resume script as well, as an example, to do something in order to compromise the integrity of the OS during resume from sleep. So from repudiation, you basically claim that you didn't do something that you actually did. So if you're somehow able to, for instance, make the system forget that you had tampered with it by opening the case, then that would be a potential way of repudiating an attack that occurred on the system. And of course, for information disclosure, something that has come up with EDK2, I believe back in 2016 or so, is user passwords being left in memory. So anytime you have confidential data, you need to make sure that you securely remove that data from memory before you end executing whatever function was actually manipulating that confidential data. And of course, any sort of denial of service attack would be if they're able to make it so that the platform doesn't boot or that some component in the system no longer functions properly, then they've successfully performed a denial of service. And with an elevation of privilege, the most common example there is when somebody is able to execute arbitrary code through management mode, either through a call out or by tampering with SMRAM in a way that they're able to add their own code into the system management memory. So once you've gone through and classified your different types of attacks, you can focus on actually mitigating them. And one of the techniques for doing that is to use defense in depth. So the way that defense in depth works is that you provide complementary layers of security that work together to protect the platform or also enable you to detect when the platform has been compromised. So the point of this is to force the attacker to basically chain multiple exploits together in order to be able to compromise the entire system. And obviously, the more exploits they have to successfully accomplish, the less likely they are to compromise the system. So for example, if you have a hardware root of trust that cryptographically verifies your code at boot, and then you also are using management mode and other technologies to protect your flash part while the system is up and running, and you only allow cryptographically signed firmware updates to be applied to the flash part with a remote attestation service, then you can have several layers of protection against any sort of tampering of the physical SPI part and the firmware image that is stored on it. And if somehow someone is able to do that, even with a DEDI prog, you can tell that the attestation is incorrect or that they are no longer attesting at all to boot the platform. So those all provide several layers of security against firmware tampering as an example. One thing that is very important is to not depend on obscurity in your code in order to protect the platform. So almost every product out there, you can go onto the internet, find the firmware binaries for some update, and download them and analyze the binaries themselves. So there are plenty of tools that are available to do that. You can use ChipSec, UEFI tool, all sorts of different tools to analyze UEFI firmware. And one thing that I've noticed here at AMI is that most of the security researchers that reach out to me are actually sending me decompiled binaries. So they are looking at the assembly and whatever C code they can reconstruct from the binary image and finding vulnerabilities or potential issues there, and then using that to actually attempt to exploit the vulnerability. So they'll create some sort of test tool that will actively try to exploit whatever issue they found in the source code. So if you have any sort of password or other secret that is actually cooked into your firmware image, they're going to be able to find it. And so you can't depend on that or some obscure protocol to protect the firmware, because most likely they will figure out how that works and they will figure out a way to exploit it. Another thing to consider when you're designing your software is to make sure that you always fail safe. So for instance, if you have some security setting with 3 different capabilities, such as not secure, somewhat secure, and most secure, then you need to make sure that the code that actually puts you into whatever security state has the default case be the most secure. So it could be if no security, do this, else if less secure, do this, else we're now in the most secure section and we do whatever we can to protect the platform. And the reason behind that is if that configuration is somehow tied to like a UEFI variable, for instance, and they're able to somehow tamper with that variable and set it to an invalid value, and if you have if, else if, with nothing after that, or the final else being insecure, then they could go in there and potentially set that variable to something that doesn't make any sense to your code, and you will just skip every single security check that you might possibly want to perform. And also, you should make sure that you have same default values so that if somebody just completely destroys your NVRAM, as an example, the system will still boot. You don't want it to hang because the attacker is able to completely wipe out NVRAM. And finally, this is one of my favorites. I thought about putting an X-Files picture here. Trust nobody. Use a hardware root of trust. Make sure that nobody is able to tamper your firmware. Protect your SPI access. Measure all of your code before you run it. Lock down management mode as soon as possible, and definitely before you run any third-party option ROMs or any code that you haven't measured. Validate all your input buffers. Make sure that you sanitize strings and anything else that you do inside of management mode. I would say you should do that everywhere, but it's especially important in management mode. And finally, the most important thing is to follow secure coding standards, which I believe Dick is going to talk about now.
Yeah, thanks, Eric. That's a perfect lead into Dick's section. Because now we get into secure coding.
Anyway, go ahead.
Yeah. So I was going to ask you, what do you think your most common problems are when you get into secure coding and code reviews?
Yeah, great lead into my first slide. As an engineer and architect for Phoenix Technologies, the last few years I've been attending Black Hat and DEF CON conferences to get a feel for what the guys out there who attack firmware are thinking. And it's very interesting. Vast majority of attacks, even those that use very clever hardware techniques, etc., they always seem to get access to the system via buffer overflow. You talk to the row hammer guys who figure out how to attack memory by banging on it, they, etc. There's very many different approaches to attacking hardware, but somehow they have to get access to the system, and usually in some privileged mode, they elevation of privilege kinds of things. And in nearly every case, they first get access to your system by a basic, simple buffer overflow, copying, providing too much data for a buffer, overflowing and inserting essentially their code or their configuration information into your memory space. So this is the number one thing. It's the cause of nearly every failure out there, at least the initial step in those failures, or the vulnerabilities. So please look for these. Use CopySafe services to copy data around, etc. Other common coding errors that cause problems, arithmetic overflows and underflows similar to buffer overflows, leaving in manufacturing backdoors. Many of our OEM customers who use our firmware or our manufacturing department of different organizations ask us to leave backdoors to make it convenient for them to configure and install firmware on systems. But the last step of the manufacturing process should always be removing, closing off, disabling, wiping out special passwords, whatever is required to close those backdoors. That's we see over and over again that occurring where people leave those backdoors in there, just forget. Cryptography, don't do it yourself. There are plenty of examples of good cryptographic algorithms, implementations that you can use. We see too many times where people try and say, well, I'm clever, I know how to come up with this, or I did something back in college that was really clever. I'm going to grab that routine and nobody will be able to break that. Well, turns out the professional mathematicians are really good at this, and we shouldn't be bypassing them and trying to implement it ourselves. A very common error is race conditions with time of check versus time of use, where you check a variable or an input value or something and say it's completely valid, and then you don't use it immediately. Actually, the gap can be even just a few instructions, and somebody gets in there and modifies the value before you actually use it. So this is a very common situation. You need to check your inputs and put them in a safe location where they can't be modified in any way. Memory leaks, a good denial of service attack. Just try things over and over again and see if it leaks memory and it causes a hang. So you can cause an easy denial of service by exposing a memory leak. Next slide. Reducing attack surfaces. In your threat model, you'll discover what are likely attack surfaces that could be used by the bad guys to attack your code. If you don't need a feature or a service in your code, take it out. It feels good to add bells and whistles and neat new features to our firmware, but gee, what is firmware supposed to do? It's supposed to initialize hardware and boot an OS. That's really all it needs to do. And we need to be careful about adding WYSI features to our firmware that are really not needed. Does our firmware really need to access the operating system's disk partitions? Does it need to do email out of firmware? Are there other ways to do these things? So if it doesn't have to be there, consider leaving it out. Don't just say, hey, I know how to do this, I can add it, it'll add value to my product. Does it really if it opens up security vulnerabilities? If you do have networking enabled, and you probably do in modern firmware, make sure that ports and services that are not being used are shut off. Study the threat model for ways to improve your attack surface, reduce your attack surface, and for the interfaces that you are required to provide, make sure you fuzz test them, which we'll see in the testing section coming up. Next. You should use the available compiler features. Most IDE compiler tool sets provide some pretty clever static analysis tools that will review your source code for you and flag potential areas. You should do your very best to remove any reported flaws that those static analysis tools provide. There are many additional static analysis tools, I'm not going to list them here, but that are available. You can add runtime checks to your code that the compiler will put in for you. You don't need to code. Things like stack cookies to make sure that you didn't do stack overflows, heap checking to make sure you didn't overflow buffers in your heap, setting data regions as no execute. Most processors now have the capability of flagging certain pages as not executable. So if somebody overflows a data buffer and puts code out there, it still can't be executed. Most of these features are available in the open source Tiano Core implementation, but they're not enabled by default. Some folks just enable them during testing, during fuzz testing in particular. That's great, but consider enabling them in your shipping products. The danger, of course, is make sure that when these failures are detected in this space, that they don't result in a denial of service. You don't want the system to essentially just assert and stop or go into an infinite loop or something like that and cause the system to die. What you want to do is report the failure and potentially reset and start over again. Next. Firmware, special considerations. Firmware typically manages the system in management mode, we refer to here. That's the term UEFI has centered on for the various different implementations, SMM and Intel platforms, Intel architectures, the trust zone for ARM platforms, and there are others on different CPU types. But these are ring -2, much more protected area than your operating system. And the firmware of your platform must manage these. And so there are special considerations here, particularly once you're in management mode, you can't call out of the protected memory to unprotected memory because somebody may have modified that, and now you're running unprivileged, you're running unprotected code in privileged mode, which is a very bad thing. You must validate all input parameters and buffers and things from that are passed to your management mode to make sure that they don't touch areas outside the protected region. And this is a particularly notorious place where we have seen the time of check versus time of use vulnerabilities pop up, where a parameter is passed to management mode, it's checked, and then at a later point gets used, but it's sitting out in unprotected memory, and it gets modified in a race condition between the management mode code and normal code, and bad things happen. Because this ring -2 code is so critical that it definitely needs a special security-related code review, particularly when it's supplied by an external supplier that's not a member of your team. If you're getting it from an OEM or whatever, you have no idea what their skills and experience are, whether they followed proper procedures, so it warrants a definite code review. Next. Continuing the special considerations, secure firmware update. We've talked about that in the earlier slides, but you need to make sure that your code is updated securely. We really are encouraging end user customers to update the firmware on their system to make sure they get the latest and greatest and with vulnerabilities fixed. But there's still a danger there if the firmware update is not done correctly. There are common open source implementations of firmware update. You should go ahead and use those whenever possible. Try not to roll your own because the chances of making errors are great. Where the open source versions have been reviewed endlessly and most bugs found and fixed. If you do a custom implementation, look for vulnerabilities that have already been fixed in the open source versions of the same thing. We find that developers tend to make the same mistakes. Even if they're doing the code independently, if one developer makes a mistake, chances are really good that another developer will make that same silly mistake. So reviewing fixes for open source versions can give you hints on what to check in your own code. Make sure you enforce signed capsule updates, enforce rollback protection so you don't roll back to a less secure version. Make sure that when you ship the product that you're not leaving something in a manufacturing mode or attempting to use a wide open manufacturing mode for field updates. There are better ways to do updates of flash parts and all that than turning on a manufacturing mode to do it. And also for your passwords and security features, you should be using, if you sign your own code and provide your own public-private key pairs, those kinds of things, you need to have either a hardware security module as an appliance that securely stores your private passwords, or a signing authority that will handle this for you. It is incredibly common for somebody to place their secure private passwords passcodes, whatever, your secure keys on a server inside their facility and think that they'll be okay there, that no one knows where they are. And in fact, those get exposed. Next.
Yeah, thanks, Dick. I think that gave us a very good overview of trying to locate your secure issues in code before they enter your testing phase. But just in case they make it to testing, Brent, testing firmware, how hard could that be?
Well, it really depends on which piece you're trying to test, whether it has hardware features or it's just software. If you go to the next slide, there's some special considerations when you're testing firmware. So an assert in firmware actually usually produces a GP fault, which goes to a function called CPU dead loop, which is literally just an infinite for loop. So if you hit one of these conditions, it will be considered a hang and essentially a denial of service. So we want to try to avoid any of these things within release firmware. So a lot of times the asserts will be compiled out, and also as Dick pointed out, the use of some of the compiler protections aren't put in. There's also size constraints within firmware. So the SPI is usually 8 to 16 megabytes, and adding additional bloat to the code or security enhancements, etc., will make you go out of the flash size. So it's hard to do that. And a lot of tools don't inherently work with firmware out of the box. They need special modifications, especially the dynamic analysis tools. Even some of the static analysis tools, as we'll talk about a little later, can have trouble. So, next slide. So if we think about security testing, just in general, usually you have a program or some kind of interface with intended functionality, but when you actually run it, the functionality may differ. So what you're trying to do is you're trying to ensure that the traditional faults are handled correctly within the static code. The unintended or undocumented functionality can be found out with more dynamic analysis or runtime. And then you're also looking for missing defenses, which usually will be within the static. Poor defenses can be in the static or dynamic, and then extra functionality usually you'll find within dynamic. So this could be within static when the code is compiled into the binary, the compiler may do things that you don't actually see in the C code. So you have to look at that as well. Next slide. So some of the things you can do, Dick kind of talked about this, so we'll just go over it at a high level, is targeted code review. So if you understand kind of your trust boundaries, as Eric mentioned, you can go through and you can look for where you may have trouble in the code and ensure that secure coding practices were followed. We have UEFI has some resources, or EDK2 has resources that people have written down. If you see the links. And where are some places you might want to look? You may want to look where there's a lot of old code. So, for example, if a feature was introduced in 2012 and hasn't really changed, it may be good, but if it hasn't changed a lot, it may also be bad because the security assumptions may not be the same anymore. Code that runs at elevated privileges, I believe we've talked about that with a lot of detail. Code that has previous vulnerabilities, we want to make sure that the vulnerabilities aren't reintroduced. Complex code, so anywhere there's a lot of conditionals or a lot of math, a lot of copying, etc., you may want to invest a little more resource in that. And then code with high number of changes. So if you have code that is continually changing within a certain time period, that's also a good target to look at. Next slide. And some of the things you're looking for are the secure coding practices that Dick had talked about, and also just within the CWE, 12 of the top 25 are related to C code, and C code is used heavily within UEFI. Next slide. Another testing method is unit testing. So try to develop unit tests for all your interfaces that you can. Your unit tests should have some positive and negative tests of what input should be accepted, what input should be rejected. You should try to enable the unit testing within your continuous integration or continuous development process. So instead of waiting until the validation team gets it, try to do it with your daily builds or something where you're not expecting to do it at the end. And try to use it to catch problems early. And try to use it when problems are found. So if a bug has been reported, try to integrate that into your unit testing so you don't continually have the same problem pop up if for some reason code gets rolled back. There are some existing frameworks available. So the host-based firmware analyzer provides some unit testing and some dynamic analysis as well in one product. There's a link at the bottom if you want to read it look into more details. Next slide. So some other tools you can use, static analysis tools. Each static analysis tool will be better at searching for different bug classes and bug types. There's not a recommended one to use, but you should use a variety. The one caveat there is sometimes they have to be tweaked and tuned because the compilation process is not as straightforward as some other environments. In terms of fuzzers, fuzzing is great when you can provide erroneous data or just random data to interface or input. Some common ones are libfuzzer and AFL, which are actually put into the host-based firmware analyzer. Code coverage tools can be a good way to allow you to see which parts of the code are actually covered during testing. So if you're not hitting certain pieces of code, it may be dead code, or you're not providing correct inputs to get to that code. So at least knowing that you're able to highlight different pieces of code may not make you 100% security or 100% secure, but it may allow you to find better ways to test certain inputs or change inputs to better test your code. And then there are some hardware setting validators such as chipsec, which can go through and validate that various hardware bits have been set within your system. Next slide. So some various testing methodologies that people can use. So a lot of people focus on the malicious data of how data is validated. So when you pick a module or interface, if it's external input, you should be testing it for malicious data. But also when something's leaving the trust boundary, as Eric pointed out, you should also be scrubbing it for sensitive data. Have your testers or validators look for bad patterns. So anytime that you can put in an improper type or data, anytime that there's a structure with a header and a size field, ensure that the size field has been validated. Are there empty passphrases? Are there test keys, inserts, test and dev keys, inserts within the code that haven't been removed? Is there a previous error or bug found within that region of code? You may want to take that pattern and search through the rest of the code, because this more than likely the same type of developer or thinking was used in multiple places. So just because you found it in one place doesn't mean it doesn't, exist within others. Another way to kind of think about the problem is to assume a high-risk module or interface has been compromised. Where could the attacker go from that, and what can they enable or disable? And lastly, which security features are you using, or is the system depending on, and how are they enabled or disabled, and when are they protected? So if you can kind of think about what they're doing for the system and how you protect them, you can ensure that your code is actually doing that, and that the attacker is not going to be able to get there.
Great, thank you, Brent. And again, I want to thank you for coming in at the last minute to cover for Tim, who was unable to attend today. All right, the last section we want to talk about before we go to our Q&A is response to security vulnerabilities, because if you don't actually have a plan to respond to security issues that come up in your products or to update those issues in the field, then you practically don't have a security plan. So Dick, since you work with USRT to handle vulnerability reports on UEFI, what tips do you have for coming up with a response plan?
Sure, and that's really the most important tip, is to have a response plan. I'm going to go to my next slide. Yeah, the thing is, vulnerabilities are going to happen. Mistakes get made, code problem, the world is the way it is, and we're going to have vulnerabilities. They happen. So you need to have a process in place, planned ahead of time, to analyze any reported issues, try and find how this happened, both so you can fix it, but also so you can identify ways to make sure it doesn't happen again. You need to have a team in place, pre-planned, your experts in various parts of your code identified, or whatever's necessary to analyze the problems that you found, develop and deploy a fix. Then you've got to be able to inform your customers, clients, the people who you provide your firmware to, whoever that is. You need to be able to notify them. And guess what? We all hate it, but the lawyers get involved at this point. So it's a really good idea to not wait for an emergency to actually engage with your corporate attorneys to figure out how do we want to respond to incidents? What do we want to disclose? What maybe create some boilerplate announcement documents that get legally approved to make sure that you don't get yourself into trouble by taking responsibility for things that are not really your responsibility, etc. Basically, engage with the legal team ahead of time and decide how you're going to respond to various types of vulnerabilities, what you're going to say, as far as possible. Now, every situation is different, and you'll probably need to validate your response, but identify who in the legal team you should be talking to under those circumstances, et cetera, because there's usually, it gets to be kind of panic mode. And then lastly, once you've got up through all of that, you've identified the issue, you've created a fix and deployed the fix, you informed your clients and customers and engaged with them to get this out into customer hands, et cetera. Then you need to figure out, how did this happen, and try and fix it so it doesn't happen again, and update your testing to confirm that you can detect this kind of thing in the future before it gets in the hands, before it gets released to your clients and customers. Next slide. The UEFI organization, about 4 years ago, I think, created the UEFI Security Response Team. I lead that team, and it's made up of representatives from the UEFI promoter companies and invited guests, primarily open source invited guests, people from open source in the open source environment generally, operating systems, etc. We felt like we really needed their point of view. The goals of that team is to provide a point of contact for anybody who wants to report a vulnerability to the UEFI organization. This could be a vulnerability in our spec and design. It could be potentially an open source problem in the Tiana Core open source world. It can be a security researcher or whoever who wants to report something. The problem is, of course, the UEFI supply chain, the supply chain for firmware through OEMs and ODMs and other platform manufacturers and white box builders and everybody else. A lot of times they're not sure who created the firmware for a particular platform or who to report it to. Many OEMs, the smaller ones, the overseas OEMs, don't have a security path. So the UEFI Security Response Team supplies a point of contact for anybody who wants to report a firmware vulnerability. And we'll take it upon ourselves to try and get that information to whoever needs it. Particularly, of course, the person who supplied the firmware that has a vulnerability potentially. But also we tend to notify pretty much our entire community, because in fact, it turns out that if you one company has a vulnerability, many companies probably have that same vulnerability or a similar one. So we try and notify our members to look out for things. Then we work with the member companies of UEFI to coordinate their responses to actual and perceived vulnerabilities. We do not act as a gatekeeper for patching systems or anything like that. Every company that supplies firmware, be it an OEM themselves or firmware providers or whatever, needs to get their vulnerabilities patched as quickly as possible. So we don't get in the way of that, but we work sometimes with reporters who want to take credit for a clever vulnerability they found, and really they don't necessarily want to create a zero-day attack, but in fact they want to get out as quickly as they can with how wonderful and clever they are. So we work with them to try and do a responsible disclosure. And as it says here, we work closely with the Tiana Core open source community that provides EDK2, the open source version of firmware. So anybody who has any questions, concerns, finds a vulnerability, go to the UEFI website, the security tab there, or send an email to security@uefi.org. We do provide a PGP key out there if you want to supply something that you don't want to send over the internet insecurely. You can encrypt it and send it to us that way. So anyway, please report anything you need to, or just ask us questions, whatever. We'll be happy to respond. I think that's it for me.
All right, thanks, Dick. All right, and in summary, if you were going to take anything away from the session, it's probably these 4 main points. One is that you need to understand the threat model to firmware and how it differs from other software. There's a lot of public documentation in EDK2, which we use to model a lot of this presentation. Second is, please write your code with fewer complexities and smaller attack surfaces. A lot of UEFI implementations by default deploy a lot of runtime services that may or may not be needed by every application. So you can look at opportunities for removing interfaces so that they remove that opportunity for attack. Third is, when you test, think like an attacker. If you were going to be a boxer, you would want to figure out how not to be punched in the face. So kind of look at your code that way. If you were going to attack your own code, where would you start? And fourth, have a plan for firmware updates and issue reporting, because these are things that customers are going to ask about, because there's a higher level of thinking now about security when it relates to firmware. So I want to thank all the panelists again for their contributions. I want to thank Eric Bjorgi at Intel also for contributing content to the test section. He's one of the maintainers of the chipset project. And now I think we still have a few minutes left for Q&A. So time to find out what questions we got.
Great. So the first question that we received is, what is your preferred methodology for SDL? Waterfall, Agile, or DevOps, and why?
Ooh, it's a good question. It's almost like asking which text editor you prefer, but I don't know if any of our panelists have an opinion on that.
This is Dick. The development approach, I would say in most cases, most folks are using an agile approach to this kind of thing, but that is a dangerous approach. It's when I also do some teaching in this area and in software engineering generally, and it seems that when you have a critical area that needs to be highly secure, that planning is important, and doing that kind of development in an agile approach where you essentially quickly respond to needs and produce code quickly and ship it essentially, and then fix it later if necessary, is not generally a good approach for life critical or security critical applications, because you really need to be able to plan and think about the implications and study your threat model and that kind of thing. So while we're all sort of feel like waterfall is evil and agile is the thing going forward, this is a case where a more planned approach makes more sense to me anyway.
Great. Second question, what is your opinion about using formal methods such as model checking to verify security properties in firmware?
This is Brent. I think formal methods is a good approach. However, it's a very targeted approach, and a lot of assumptions need to be made. So I don't believe it can happen for all parts of firmware, but for security critical pieces, it is a good approach.
Formal methods are a less mature approach at this point. It's an area in development, I think, and it's very difficult to do on large quantities of code. But I think it's actually would be an excellent approach to view what I was talking about in my coding slide about code reviews for that management mode code, that critical small section of code that's so important. Formal methods might be a really good idea to apply to that kind of validation and checking code reviews, et cetera, of the management mode code.
Great. Last question, how prevalent, applicable, and practical is the use of fuzzers and fuzz testing for low-level firmware components in SDL?
Oh, that's a really good question. This is something that Brent and I have actually looked at a lot over the past couple of years, because we've looked a lot at using fuzzers in UEFI, but most of the fuzz techniques that are available were designed originally for upper level software. So the place where we found the best application is in unit testing specific components before they are integrated into UEFI. Because of the driver model in UEFI, you tend to have dozens of individual components that are compiled for the PEI and DXC layers. And fuzz testing seems to be most effective on verifying interfaces on those low-level components before they're fully integrated. Brent, I don't know if you wanted to add anything on that.
Yeah, we talked about it a little bit, but it's hard for some things because I think Brian touched on it. Some of the instructions, such as the hardware-based instructions, like if you do an MSR or an IO, and you're expecting some kind of input back, aren't modeled within fuzzers or symbolic execution environments. So it takes some time, and you need either a special emulator or to work directly on the hardware, which, if you do something wrong, you potentially can brick it, or, you need a DediProc to recover. So it is an area that's being explored, but it's harder when you start to interface with the hardware.
Yeah, I would recommend, if you're interested in that, look at the host-based firmware analysis tool that we linked to earlier in the presentation. If you just Google search for Tiano Core HBFA, you should find the documentation for that, and that goes into the methodology they use for applying off-the-shelf fuzzers like Peach or AFL to firmware components. And I do believe that was our last question we're going to take online. Our folks that were setting up the webcast are going to help us collate any questions that were not answered, and we may address them in a future blog at uefi.org. If you have any other questions, please feel free to go to uefi.org, find the contact form, and contact us. And let us know also if you're interested in any other topics for future webinars. We try to have one of these about every 3 months. Again, thanks to our panelists, thanks to our organizers at Nereus, and thanks to you for spending an hour with us talking about firmware security. Have a good day.